Hello and welcome to Astronomy's Deeper Perspective. In this presentation, we're going to talk about the planets being what had formed from stars' raw materials or stars' remnants, such as from the outer layers of a white dwarf, or also next to the outer layers that have been shed either by a white dwarf or a black hole. Previously to becoming a black hole, the star at its latter stage for supermassive stars actually implode and explode in a supernova, providing more heavier materials, more heavier atoms to create actually planets and newly formed stars. So it provides substances for the creation of planets and even younger stars. Let's start right from the beginning. So at first, we understand that the world's universe ages were framed and created, formed, put in order, equipped for their intended purpose by the word of God, so that what is seen was not made out of things which are visible. This is a powerful verse in Hebrews, book of Hebrews 11, verse 3 in the Amplified Version, which is in the New Testament in the Bible. So let's break it down. By the worlds, the verse is referring to multiple dimensions actually. And this includes the ages or the time variable. All of that was established by God for an intended purpose and designed in order, the order which is governed by the laws of physics. And even these laws, like gravity, were created by God as well. By the worlds, the verse is referring to multiple dimensions. So when it mentions the worlds, it's referring to multiple dimensions, or what you also would call a multiverse. And this includes the ages, which is the time dimension, the time variable. All of that was established by God for an intended purpose and designed in order, the order governed by the laws of physics. And even these laws, like gravity, were created by God as well. Now, the other part of the verse is very interesting from a scientific perspective. So that what is seen was not made out of the things which are visible, which conforms with the physical matter being transformed out of pure energy and heat. This is also Einstein's theory of energy transforming into matter and vice versa at the speed of light. And by the way, even secular science sides with the fact that what is physical was made from what is not physical. Another part of that is the physical matter being actually the byproduct of energy, pure energy, and heat. And by the way, in the book of Genesis, God created out of nothing the heavens and the earth. We will get to that. Heavier matter coming from invisible matter, another part. If we look at the fusion process inside a star's core that takes place at around 1.4 billions of degrees, for some fusion reactions, not all of them, actually the fusion starts from tens of thousands of degrees, around 10,000 degrees, and it starts reaching millions. By the millions of degrees, heavier materials, heavier atoms starts fusing within the core of a star. And of course, as the heat and the temperature rises, it allows the fusion for even heavier types of matter, such as silicon, of neon, of oxygen, etc. The fusion process that was initiated by the high pressure and high temperature of H1 protons, which is the first matter of the universe, if you will form deuterium, then helium, then heavier atoms gradually in the chain fusion reactions, one after the other. So forming the heavier atoms until it goes all the way to iron and nickel, which are the heaviest ones. All coming from one hydrogen atom, H1, which is invisible, by the way. So physical matter came from what is not seen indeed. Let's go down into details over the process that formed the first stars and how the planets were made out of that. In the first verse of the book of Genesis in the Bible, in the beginning God created, the word there is formed out of nothing, by the way, the heavens and the earth. The heavens refer to multiple dimensions, and the earth refers to the first form of primitive matter, not necessarily the earth as we know it. What also came with them are the laws of physics. The word beginning is an indicator that it wasn't always there, but it was created, or it all came to be from a starting point, from a point of Genesis, before it came into existence. What you would call time-space fabric has actually a beginning. Now, in the early stages, there was a large spread of nebula, as I believe made of the primitive matter scattered with some form of inherent energy to it. The gravity then started pulling the first type of matter together. That's the type of energy. I would rather call it potential energy. It had some potential energy which is in the gravity of these primitive atoms. The gravity then started pulling the first type of matter together, which is H1 hydrogen. And as they clamped up, the pressure increased, and with it, the temperature, leading to heated clumps. Protostar. Then, what happened next? As high pressure increased, this increased the heat of the assembled hydrogen atoms, leading to what is called the protostar, the first form of a star that has an increasing or rising temperature. It started glowing, and gradually that nucleon, if you will, that core starts forming for that first type of stars. Main sequence star. After that, it kept heating up as it attracted more and more matter to it due to its increasing mass, and as a result, the increase of its gravitational force, of course. So it got to a point where the heat became so intense, reaching around 10,000 degrees. Which is the correct condition for the fusion reaction to start. And the protostar at this point became a fully grown star, entering what is called the main sequence. You know, the stars that you see the most in the heavens are main sequence stars. They are fully grown up. During that phase of a star's life cycle, these or three main reactions contributing to energy generation or reproduction, if you will, occur, but also other reactions take place after the third, creating harder core materials. Let's go into that. The first reaction is the fusion of two protons, two hydrogen H1, leading to the formation of a heavier element, which is the deuterium, plus releasing a positive charge, positron, plus one neutrino, which is a neutral particle. A deuterium 2H, after that, fuses with a proton, giving a helium He3. Another thing that happens in that reaction, which is the release of a gamma emission or a photon, which is, by the way, responsible for the light production, for generating light within a star, like our sun. So mainly the second reaction is the one contributing, or the one leading to the generation of light. Now, helium He3, in the third reaction, two He3 actually, they combine to form helium-4, which is a heavier element, of course, and two protons. Now, within the third reaction, these two protons will participate in recreating the reaction cycle, meaning that they will be added to the other protons to restart the fusion cycle among these three equations. The overall equation, if you will, is for H1 protons will lead eventually to a helium-4 plus 2 positrons emitted plus 2 neutrinos plus a gamma radiation, a gamma wave. And God said, "Let there be light," and there was light. Genesis chapter 1 verse 3. Here God spoke light into existence, but technically speaking, if we break down what is happening, the power of God residing in a sound frequency carrying massive energy. You know, sound is a form of energy. That sound frequency carrying massive energy led to the fusion processes to start and to produce the first photon, the first gamma and the second reaction by pulling matter together through an invisible force, which is what we know as gravity, which causes gas pressurization, heating up, and eventually the fusion reactions. And he is before all things, Jesus. And in him all things hold together. Now, this is an interesting evidence, if you will, that the force that held everything together, that grabbed different protons in the first early stages of fusion, that force pulling them together is actually a force from God. It is the force of the Word of God. So gravity came from God as well, and that's how the fusion started to eventually lead to Genesis chapter 1, verse 3, eventually producing light, generating the first photon, the first light, which is in the second reaction, by the way. The third reaction is the last reaction, contributing to refueling the sun for the restart of the reaction cycle, producing light through gamma rays. After that, now after the production of light, which is in the second reaction, not this one, the third reaction reproduces two protons, which are responsible for contributing to the reaction cycle among the first three equations, this being the third. But helium-4 itself is a heavy element that no longer produces hydrogen elements, but participates in fusion processes, creating heavier elements, from which all type of heavy matter was made, including iron being the last, iron and nickel. So, if you go to, especially in more massive stars, helium-4, which is a heavy element, fuses into carbon. So 2He4 will fuse into beryllium-8, then one beryllium-8 with helium-4 will lead to a carbon-12 and a gamma radiation. So at first, helium-4, two atoms fuse into beryllium-8, which is unstable. Then the beryllium-8 fuses with another helium-4, forming the carbon-12, which is the atom behind all organic matter, and producing a gamma ray, which is a photon. Another byproduct of the helium-4 fusion eventually is oxygen, made from the carbon. Carbon and oxygen fusion. Okay, so 2C12 will produce a neon element plus a helium-4, and you notice that the atomic number is always stable. So you have C12. If you add 12 by 12, it will give you 24, which is 20 atomic number or sum of neutrons and protons in Ne, and 4 in helium. 20 plus 4 is also 24. And by the way, also there's an equilibrium of charges between the reactants and the products. Also, the second equation, you have 2O16 fusing together to form silicon and helium. So you have 32 atomic number, the sum of atomic numbers to the left, and 32 to the right. All right, so 2 oxygen will form a silicon plus a helium atom. Silicon-28 with a gamma ray will transform into iron Fe56. This involves an alpha particle captures and nuclear rearrangements, forming elements up to nickel 56, which then decays, by the way, into iron Fe56. So the nickel will decay into cobalt 56 plus a positron plus a neutrino. The cobalt then again actually disintegrate to form the iron Fe56 plus a positron plus a neutrino. So as a summary, hydrogen transforms into helium, then helium into carbon, carbon to oxygen, oxygen to neon, neon to silicon, from which comes also nickel and iron. Now, in a nutshell, the hydrogen fusion formed deuterium, then helium, as we know. The first three reactions, helium burning formed carbon C12 and oxygen O16. Carbon burning formed neon, sodium, and magnesium. Neon burning formed oxygen 16 and magnesium 24. Oxygen burning formed silicon, which is, harder and the harder materials are forming each time, we have a reaction with sulfur, phosphorus, and others. Silicon burning formed nickel, then cobalt, then iron eventually, which is the hardest and the most stable core, actually, the most stable metal. Heavier matter coming from invisible matter. Okay, let's examine the chemical structure of a massive star that looks like a layered onion, having a weighty core with heavier elements all the way to the lighter elements as you go outwardly. As you go further from the core to the photosphere, you get lighter and lighter with the types of fusions, the type of elements that are available, and you know, the types of fusions having less requirements for a more intense temperature and heat and a more intense pressure. So if we start from the core, starting from the core, you would have the heaviest materials, nickel and iron, forming out of silicon burning. Then you go to the inner shell, right next to the core, you have oxygen burning, forming silicon and sulfur. You go out another step. That's why, by the way, it's like an onion, because it's layered, one layer after other, all the way to the core. So next shell, and we're moving outwardly here, you have the neon burning, forming oxygen and magnesium. Next shell, carbon burning, forming neon, sodium, and magnesium. Next shell, here you notice as we go approaching the surface, we have lighter and lighter materials requiring lower temperature to fuse. That's why you would have at this level the helium burning to form carbon and oxygen. And the outer shell, which is the coldest area in the sun, if you want to consider the sun, it has hydrogen burning and helium to form actually helium. Alright, so by examining this table, we notice that the closer we get to the central core, the heavier the elements involved become. Due to the fact that the gravity is stronger close to the center, and the very high pressure and hot, very extremely hot temperature allows the fusion of heavier elements such as silicon to take place, producing heavy metals like nickel and iron. But as we go further from the core to the edges, to the outer layers, you have lighter atoms fusing at lower temperatures, and heavier elements get sucked deeper and deeper inside the core as we go within the core. The point is, the core is the heaviest one, having fusion processes that are going on, fusing much heavier elements than the outer shell, where you have lighter materials, lower temperature, lower pressure, and a fusion of lighter materials leading to a little bit heavier products. Red giant and red supergiant. So as the star's fuel is exhausted because of the H1 elements running out and forming into heavier atoms, of course, the fusion process slows down. As a result, the force created by the nuclear fusion that was pushing the core outwardly, preventing it from collapsing or imploding, so to speak, becomes weak. The core contracts further and further, collapsing under its own weight and gravitational forces. This causes it to gradually detach from the outer layer because it's receding inwardly, and which now have become more distant, meaning the outer layer to the core, and are under weaker gravitational pull. These outer layers expand further, bloating as a balloon being blown with air being blown into it. So since the fusion reactions are no longer as redundant because of the intense decrease of H1 atoms, the star is no longer burning with the same intensity, and its external temperature cools down, which translates, by the way, into a red external apparel. Red is a longer wavelength, lower frequency, having less energy and temperature. Okay, because as we know, higher frequencies like ultraviolet, that's why ultraviolet is much dangerous, and the blue wavelengths have a higher frequency, thus a much higher energy and a searing heat. This is what we call for the red apparel of the older star. This is what we call a red giant or red supergiant for massive stars. Note the core is hotter than a star of the same color, meaning that if you have a star, red star, which is in the main sequence, it will be colder than a red giant. Why? Because the red giant has its core still burning and fusing heavier elements, which increases its temperature relatively to a red star within the main sequence. White dwarf, neutron star, and black hole. After becoming a red giant, or red supergiant for massive star, the latter state of a star depends on its mass, or the last stage of its life cycle. For a small star, it becomes a white dwarf, shedding its outer layers made of mainly helium, oxygen, carbon, nitrogen, neon, sulfur, argon, and other lighter elements that become the raw materials, some for new stars and others that are colder and require very high temperature to fuse, attract together to form the core of planets. And that core starts even attracting more surrounding matter that are lighter to form the mantle and the crust of these planets, such as rocks, silicon, and dust. And some ice also, some iced, if you will, gases for the planets that are further from the star. Because as close as you get to the star, the temperature gets hotter, plus there's no longer a possibility for ice to form because it evaporates under the high temperature. As for the white dwarf, it remains extremely hot due to fusion reactions that are still taking place to form heavier metals, heavier elements within the core, producing that white external glow. That's why it's called a white dwarf. This is how it appears. As the fusion eventually ends with an iron core, alloyed usually with nickel, the heat burns out and the white dwarf turns off like a light bulb, becoming called the black dwarf without any glow. So we call it black dwarf. As for supermassive stars, after the outer layer is shed, the state evolving from the red supergiant, of course. This is what happens after having a red supergiant. The core contracts under a more intense pressure and heat and a colossal gravitational force because of its very massive weight. The fact that a supermassive star previously had a much larger reservoir of protons, all of that had transformed under heat and pressure to form a much heavier core with the ability to compress the iron and nickel with other atoms even thinner, even to a smaller volume. Eventually the core implodes under its own weight, so it crashes down under its own weight and then rebounds back, causing a huge explosion called supernova, releasing all types of matter that were in the core, that were created on the inside of the core, including heavy metals such as iron and nickel. So not only not only the outer layers were shed, okay, to form the substance for newer stars, but also the core itself had exploded. So what is left is what we call a singularity, which is the black hole, a tiny point of matter having an infinite density, okay, that we call a black hole. This singularity can absorb everything that comes near its proximity. However, before becoming a singularity, when it had exploded, the matter that was on the inside, much of it, went out, okay? And it partakes in forming for, heavier metals, heavier atoms. They partake in forming planets, okay? And as for hydrogen and helium, they participate in creating newer stars or younger stars. Now, for medium-sized stars, the explosion leads to a neutron star. Okay, let's continue. So, everything released from a supernova and even white dwarfs outer layers become the nebula providing raw materials, participating in creating new stars for lighter substances such as hydrogen with some dust and lower weight materials, and planets for heavy weight elements, that no longer fuse, that require much higher intensity and pressure to fuse. Actually, they have fused to their latter stage, so they assemble together, forming the planets, okay, because they are colder and there's no longer a possibility for their fusion. The black hole resulting from a supernova, the neutron star, or even the white dwarf will start pulling on the surrounding gases and matter, usually in a spiral shape, okay, due to the rotation, the evolution or revolution rather of these matter particles around these dying stars. These will start rotating around these dead stars while attracting matter during their journey to form newer stars and planets around these stars. Okay, and by the way, these dying stars will create the galaxies as we know them. For the planets in particular, those who are close to a star formed by heavier elements gathering together like iron, nickel, silicate, and rocks. Why? Because heavier elements rotate closer to a star due to their gravitational forces pulling them closer to the star's gravitational field. Okay, because as we know, F equals Gm, G small m, big M over R square, R being the distance from the star to the planet. Small m is the mass of the planet rotating around the star. Big M, the mass of the sun or the star. The sun is actually a star. Okay, and G is the gravitational constant, which is 6 point something. Okay, I don't actually recall it right now, but the point is, when you have a more massive or heavier elements around the star, they would have a greater gravitational pull into the center, closer to the center of the star. So for heavier elements, again, gathering together like iron, nickel, silicate, and rocks, heavier elements rotate closer to a star due to their gravitational forces pulling them closer to that star, and that's why they are hotter and heavier. That's why they form planets like Mars, like Mercury, they are hot and heavy. Meanwhile, the lighter elements like gases, water, and some dust become the chemical makeup of planets that are further from the sun. These will have some iron and mostly silicate in their core, but the mantle and the crust are mainly made out of frozen gases and water. Okay, but you notice that the materials are lighter than for the planets that are formed closer to the sun or to the star, whatever that solar system is. Okay, the fact that these gases are located further away from the sun will allow them to freeze together, okay? That's why they can ice up, because they cannot be, due to the vast distance from the sun, they won't melt away or be evaporated due to the sun's radiation. So this allows or creates the perfect environment for these gases like nitrogen, methane, water vapor. So they will freeze up while trapping within them some dust, some rocks. Okay, of course the rocks will and heavier elements would go further and further into the core due to the gravity forces, but the ice and other lower weight materials will form the mantle and the crust for these planets. An example for planets like that is like Neptune. So it's a lighter planet in mass overall, or it has lower density and fly further from the sun. Asteroids. Okay, so asteroids, as I suggested before, these are the broken pieces of a former planet. I know it might be a bit controversial for some, but I personally adopt that theory that asteroids are the fragments of former planets given their irregular shapes. That implies they didn't form from an equilibrium process involving gravity and axial rotation around, a specific axe, unlike the planets. But anyway, let's list what types of asteroids do we have or do we know of. First, you have the C-type, which is carbonaceous, okay? This asteroid is mainly made out of carbon, clay, and silicate rocks, which gives it a black charred color with a low albedo. Low albedo means that the intensity of light that is being received from it is much higher than the intensity of light reflected from that asteroid. In other words, there's too much light absorption. So few light that is being received by the asteroid is reflected back to allow us to see what that asteroid is looking like. It makes this type 75% of the asteroids that are within the solar system based on studies, which makes sense if we're assuming that asteroids are former planet pieces, given that the C-type would have been a part of the crust or the mantle. All right. S-type, which is silicaceous, made mainly of silicate minerals and some metal, like nickel or iron. It probably had been a part to the mantle and close to the core. Here, mantle, it's a typo. M-A-N-T-E-L. Okay. So it should be written. Third type is the M-type. M stands for metallic. So this type is composed mostly of nickel and iron. It has a high albedo, meaning that the power that or intensity of light that is being received is mostly reflected with a very low absorption. By the way, these, just like metals, are highly reflective to radio waves. This is how you identify the existence of metals in this M-type asteroid, because they reflect radio waves very well, just like the antennas that we have on Earth, which are of a metallic composition, of a metallic chemical makeup or structure, if you will. So they are very reflective for radio waves due to their metallic structure. Its composition also suggests that this type was a part of the planet's core that broke off, because it's mainly metallic. It's made of very heavy metals, mainly iron and nickel. Okay, now other less common types are the D-type, which is dark reddish, probably due to oxidization, like rusting of iron due to the former presence of water, and possibly rich with organic materials, such as, some sea carbon. P-type, very dark, very reddish, with unknown composites. And the V-type, which is mainly volcanic basalt surface. Okay, it's made out of volcanic surfaces. The basalt, as you know, is a rock, a type of rocks that is formed from volcanic eruptions. All right. So thank you. This is all. Thank you so much for watching.